section 9.4 is going to talk about odds and expected value. Okay, so you mentioned the word odds a little bit ago, Brendan. And so it is different than probability, but it is related. So that's where we're going to start. If we have P of A being the probability event occurs, and P of that A bar being the probability that it does not occur, then the way we find the odds of event A is we find the probability that the event happens, and we divide it by the probability that it doesn't. That's what odds are. Okay. Now there's another formula, there's a couple others. I could actually write this differently as 1 minus the probability of A on bottom, because just like we talked about in section 1, the probability of A complement is 1 minus the probability of A. There's one other way that we could do this, and it's often the one that we actually end up using. Do you remember this notation? This is from Math 1. What does that N with the parentheses mean? Remember? What do you think it might mean? P stands for probability. What could possibly N mean? Be prepared for earth-shattering. It means number. Isn't that exciting? N for number. Yeah. It means the number of items. Okay. So when we talk about N of A in Math 1, we talk about this phrase called cardinality. It means the number of items in the set. So if there's something where you can actually count the physical items, like you don't know the probability of something happening, but you know that number of ways that it can, you can take the number of ways that it can occur, and you can divide it by the number of ways it doesn't occur, and it will also equal the same odds as if you had done the probability. So these are the odds of event A occurring. We've also got the odds against event A occurring. And all we have to do for this is we turn our fractions upside down. Use blue. So we would do the probability against, that is the probability that the complement occurs, divided by the probability that the actual event would have occurred. And I can flip up all my fractions. So this is 1 minus the probability of A over the probability of A. Or I can write this as the number of ways that the complement occurs divided by the number of ways that the event occurs itself. This is really a ratio. This is what we really think of a lot of times when we think about a ratio. Okay? So instead of considering like the number of girls to the whole class, we would consider the number of girls compared to the number of boys. Something like that. Okay? So we're going to do one with marbles. It is marbles. Alright, from a set of 8 marbles, we have 5 red and we have 3 white, and we're going to choose one at random. Now the first question is something we've done before, right? It asks for the probability. So what is the probability that I will choose a red? 5 over 8. So when I do probability, I'm doing a ratio, a comparison of the number of ways whatever my event is can happen compared to the number of ways anything could happen. So in this case, I have 5 red marbles out of 8 marbles total. Right? Part B is different. It asks about odds. So what are the odds that I choose a red? It's 5 to 3. And again, anytime we're doing ratio, you could write it in this way, or even like this. As long as it's reduced to its simplest form, we can still write it in any of those varieties. Okay, so 5 to 3. 5 ways it happens, 3 ways it doesn't. So odds is always this comparison of it happening versus it not happening. Happening, not happening. Okay? All right. Oh, I should have asked you. I didn't. Let me go back here real quick. You don't need to flip back, but when I did the odds down here, which of these different ways of doing odds did I use? Did I use this first one? Or did I use the second one? Brenda's right. I used the second one. How do you know? Or how did you decide? I counted the number of marbles, didn't I? See, if I were to have used the first one that I circled in green, what I would have really done is I really would have said 5 out of 8, because that's the probability that it happens. And I would have compared that to 3 out of 8. And then I have one of these complex fractions, and I would have had it simplified. It still would have given me 5 over 3. Right? right? We did this reciprocate, we do the reciprocal, we multiply, flip to multiply, this, that. We'd still get 5 over 3. Okay, so it really does work either way. This next one, though, it's more helpful to talk about it in terms of the probabilities of things happening compared to the number of things happening, because we don't have a number of things happening on the next example. We only have probabilities that we're comparing. It says if the probability of rain for the day is 60%, that is a 60% chance that it will rain, what are the odds, against it raining? So make sure that when you're looking at these problems that you're very clear about which one they're asking you for. Is it odds for or odds against? So what I'm really wanting to find out here is I'm really wanting to find out that the odds of it doing what? Of it not raining. That's what I'm wanting to find out. Odds of it not raining. So when I'm doing my comparison, I want to know the probability that it does not rain compared to the probability that it does rain. Does that make sense? Whatever the odds are, that option, that desired outcome, in this case not raining, is what goes in the numerator. So what is the probability that it doesn't rain? 40%, right? I'm just going to do it with the percents that were given. So 40%, or do it in percent since they were given. What's the probability that it does rain? 60%. Now, in a very real way, those percents, they cancel each other out. And this reduces too, doesn't it? What will it reduce to? 2/3. So there is a 2 to 3 odds for it to be not raining today. It's not a probability, it's not a 2/3 probability. It's a 2 to 3 odds. Before we get to 9-8, let me just ask you, where have you seen odds used before? This is something that's used in real life. In betting. You see it used in betting. Horse tracks is really common. Anywhere else you've seen them? They will usually give you odds on gambling for other things too, like football games. People bet on football games. Odds are used, okay? And then they use those odds to determine what the payout is for certain things and what risk you take it and so forth. But odds are what are used in there. Could they use probabilities? They could, but odds is what they do use. Okay? So these are common concepts. Now, I told you there was a relationship between odds and probability, so we're going to take a look at that. So if we have the odds of an event E and they are m to n, then the probability is m over m plus n. And then if the odds against are m to n, then we have n over m plus n. And those are great formulas, and I encourage you to look at them and to think about them. But in reality, when you actually use them, you'll reason them out. So let's take a look at one so you can see what I mean, okay? So we've got a 3-child family. We did this a minute ago in the last lesson, didn't we? We've got a 3-child family. We did it with Huntingtons and not Huntingtons. We didn't do it with boys and girls, but we can still do it with boys and girls. So if we were to do three branches of a a tree diagram, and these are all boy-girl issues right here. So here's boy, girl, boy, girl, boy, girl. All the way. And we know from the last lesson that these all are 0.5s, right? Okay, so, all right, just for consistency, let me fill them all in. All right, they're all 0.5s. And this one says the odds of having all three, or all children the same gender. All the same gender of children. So we can compare, what we want is the odds of the same. So if I think about that description, how could I find the odds of having the same children? Or even the number, right, Brendan? I could do the number of ways that I get the same children over what?
The
Is
number
it?
that you don't.
This one's the number that I don't.
Yeah.
We'll need what you're doing on part B, or no, I'm sorry, it's not even on part B. But we'll talk about that in terms of that in just a second. So what are the number of ways, or how many ways do I get the same gender of children?
2.
There are 2. I can either have all boys, that's my top branch, or all girls, which is my bottom branch. There are 2 ways that I get a family that has all same gender of children. How many ways do I not get that?
6.
There are 6. There are 6 ways that I get some combination of boys and girls. And if I reduce this, I get 1/3. So there is a 1 to 3 odds of having a family that has 3 children all the same gender. How can I find the odds against? What does that mean?
That'd be 6 to 2, wouldn't it?
Which
Or
reduces
3 to 1.
Right. All the odds against is it's the reciprocal of the odds for an event happening, right? So the odds against the same gender would be the reciprocal, so 6/2 or 3/1, and resist the urge to make up the number 3, because then it loses the effect of what it actually means. You still have to leave the over 1 part in this case, okay? So there is a 3-to-1 odds against having all the children be the same gender. Now notice this is very different if we were talking about probability. Not very different, but there is a difference. What if we wanted the probability of having all the same gender?
And you would take the total number.
So I would have the same
So,
2 on top, right?
2 and then 8.
And 8. So let's talk about where that 8 comes from. Where did that 8 come from? And why isn't it 6? What happened? Right. This 8 is the 2 that are the same gender plus the 6 that are not all the same gender. That's where that 8 is coming from. And that's where those formulas are pointing out right here. Is that I can take these numbers, m plus n, and that together is going to equal the sum of the events happening. Right? That was the m and the n here to begin with. Okay? So that's what that's referring to. I think there's one more that relates these ideas together. It may be further along. We'll get there again. Okay. Expected value is the other topic in this section. Expected value is used also in gambling, but it's used for other issues as well. So you're going to see a few of those come across our plate here in a moment. So if the possible outcomes for an experiment are A1, A2, A3, all the way up to AN, okay, with probabilities P1, P2, all the way up to Pn, then the expected value is capital E, and what we do is we multiply the outcome times its probability. And we add that to outcome 2 times the probability, and outcome 3 times its probability, all the way up to the final outcome times its probability. So notice this. In order to make sense of anything that was written, everything on the right-hand side has to be a number. Right? I can't multiply girl, girl, girl times 1/8. Does not make sense. So in order to be using expected value, we have to be talking about something that has a numerical value. Right? So that's one key thing to realize. The other issue is that a game is considered fair if the expected value is 0. So this isn't that it's not fair because I didn't win argument that my children say, right? The son is just now learning to play Uno, and it's always not fair. It's not figured the game out quite yet, and so he loses a lot. And of course, it's mostly luck. So it's not fair in his mind if he doesn't win. That's not the kind of fair that we're talking about here. And we're also not talking about the kind of fair like legitimately say it's not fair in life if X, Y, Z happens to me and not to you. Okay? So this has a mathematical definition. It is fair if when we do this multiplication now, it equals 0. So we can really assess fair, not fair. It's very objective. There's no subjectivity involved. Okay? All right, let's take a look. On a roulette wheel, have you guys seen a roulette wheel before? Okay, so think like Wheel of Fortune, or it's the spinning wheel that goes around. On the roulette wheel, it has the numbers 1 through 36. They're alternating colors of black and red. And then it also has two spaces on the wheel that are green. And those green spaces are the numbers 0 and 00. Okay, everybody good so far? Okay, so we've got this image in your mind. One way to bet is to bet on a single number. So you bet that this number is going to occur. There's other ways to bet. You can bet on black, you can bet on red, you can bet on green. Okay, so the example that we're going to do is we're going to bet on a single number. If the ball lands on your number, you get 35 chips from the attendant, plus the original chip that you paid to play the game. Okay? So you pay one chip, you either lose the one chip, or you get that one chip back, plus you get 35 more. Okay, pretty good so far. Okay, first question. What is the probability that the ball will land on 0, 0? 1 out of 38. Yes, 1 out of 38. Where did the 38 come from? The 36 place, the 36 numbers 1 through 36 plus 2 more than 0 and 0. So everybody good with that probability? Okay. All right. So I'm not joking. My in-laws are wonderful people. My father-in-law is an amazing carpenter. He's a fabulous contractor. He's a very smart man. He has a Bible degree. He's a pastor before. He sings. He's a great guy. But they view going to casinos and things on occasion in a very much like you probably would view playing video games at a store. Okay? It's not a problem for them. They don't have an issue with it. They go, they plan to lose a little bit of money, and they leave, and they had a good time. But this one I don't understand. He goes by a roulette wheel, and he looks at they have a board next to roulette wheels. And the board will have the last, however many, I don't know how many it is, it may change based on the casino, I don't know. But they tell how many, what the last rolls were, what the last spins were of the wheel. And he looks on the board, and he says, if it doesn't have this number on it, and we're using an example of the 00, he does it actually a little bit differently, but this is very similar. If it doesn't show a 00 in the last however many of the spins, then he'll place money on it. He will bet that it's going to show up 00. Does that make sense? Oh, it doesn't make any sense? Because the odds and probability is the same regardless of what's happened recently, right? Okay, so we're going to do it. We're going to do the numbers out to show why this doesn't make sense. All right, so if he bets one chip and one chip is worth $10, we're going to find the expected value of his bet. Okay? So there are only two things that can happen, really. He either can win or he loses. Okay? So I don't need a tree diagram, or I don't need to discuss how many different options really happen. There's really two options. There's really two outcomes. I either win because it lands on 00, or I lose because it lands on anything else. Everybody with me on that? Okay. So when I'm finding my expected value, I'm only going to have two things that are going to be added together, because there are only really two outcomes. There's the winning outcome and there's the losing outcome. Right? So let's do winning first. If I win, I need to actually multiply two numbers together. If you take a look back at the slide before, the two numbers that I need to multiply together are the outcome, that is what ends up happening in my personal life because I had that outcome happen, times the likelihood that it will happen. Okay, let's start with the likelihood. So what is the likelihood that it lands on 00? 1 out of 38. We already did that, right? That was part A. If it lands on 00, what happens to my pocketbook? My father's pocketbook. He gains $350. Does he gain $10 that he bet? But will he earn $360? He already paid out 10. He will earn $350. So the way you want to think about this is, before I made my bet, I had X amount of money in my wallet. Okay? After I made my bet, I have this other amount of money in my wallet, and I want to figure out what the difference is between the two. The difference is between the two on this problem is $350, right? Because I have 35 chips that I actually earn on top of the one I already played. Because the one I already played didn't change. I had the $10 in my wallet before, I have a $10 back in my wallet. Okay? It's $350 that happened in advance. Where did the $350 come from again? 35 chips worth $10 each. Good. All right, so this is $350. winning. All right, what if I lose? So let's talk about the probability first. What's the probability that I lose? Yeah, it's 37 out of 38. It's pretty likely. Okay. What happens to my pocketbook? I lose $10. So the outcome is that I have 10 fewer dollars in my wallet, which means this is a negative 10. It's not zero. My pockets have changed. The amount of money I have to now go eat dinner is different than it was before. Okay? Now we're going to do a little bit of multiplication. Grab out your calculators if you will. And we're going to multiply these guys together and add them and so forth. And we're going to figure out what we have when we do that. So, some of your calculators will allow you to enter all of this at the same time. If so, that's fabulous. If not, you can do it in stages. I need 350 times 1 over 38. And I need negative 10 times 37 over 38. Or, we could simply notice, one of the things we could do real quick here if we wanted to, is that this is going to have the same denominator if I avoid reducing too soon. And if I do a little bit of math on top, what do I get? I know you guys know how to do this. Fractions, 2 chapters ago. What do? Somebody said. Yeah, we subtract the top. Heather's telling me it's negative 20 over 38. What I'd like for you to do is to turn it into a decimal. Why in the world would a decimal make sense on this problem? It's an amount of money. We do our money in terms of decimals. So multiply or divide this, 20 divided by 38, and what do you get? Negative 0.5 what? 526. Do I get to write 526?
5.3.
Thank you. Why in the world do I only need 5.3, Heather?
Because we're doing it in money.
It's money. Okay, so on average, if I do this game a whole bunch of times, on average, I lose about 50 cents every time I play the game. That's why it's negative. Okay, so on average, that's Bernoulli's law of large numbers. We talked about that back in 9.1. On average, if I play this game 10,000 times, on average, each of those individual bets I made would have been minus 50 cents-ish in my wallet. Okay? Everybody good with that? That's how you find the expected value. Let's do another one. Have you seen Deal or No Deal? Yes. Okay, so here's an example of Deal or No Deal, and, oh wait, today. Yeah, no, we're fine. All right. In this television show, Deal or No Deal, a contestant is down to 2 cases with equal probabilities of being chosen. One case has $250,000 in it. The other case has $1 in it. If the game is fair, and we're using this term a little bit loosely here, we're not meaning exactly what we did before, so I'll come back to that idea in a minute. If the game is fair, and you were the baker, what would you offer the contestant as a deal? So, we would do this with expected values, right? Expected value. And I only have 2 situations, right? I have the first case, and I have the second case. Okay, so what is the probability for case 1? 1/2. How do you know? There are only 2, and it says we have an equal probability of them being chosen, right? So there's 1/2 probability on the first case, which means the second case also has a probability of 1/2. What is the outcome of case 1? $250,000, yay you. Right? What is the outcome of case 2? $1. Alright, so what is 250,000 times 1/2? $125,000. And what is 1 times 1/2? It's 1/2 or 0.5. We'll go with 0.5 since we're talking about money in the problem itself, actually. And if I add these together, what do I get? $75,050. That would be a fair offer. So when we talk about fair offer on this, what we're meaning is a offer that would be just as good as the expected value. Okay? It's just as good as having the expected value. So this would be the offer in terms of the word fair in this particular problem. Your book doesn't have anything weirdly fair like that. That's just what happens when I make a problem. It doesn't exactly meet my definition. So. All right. We have one more example, but I'm going to save it for next time so you guys have time to do your